All right, sorry about that. Here's 11.1 part 1 continued. My phone rang. I'm still trying to figure out these settings and how not to have my videos interrupted. But anyway, we left off talking about the Fibonacci sequence. The Fibonacci sequence definitely has a pattern. Everything from the third term on can be obtained by adding the previous two terms. So 2 is 1 plus 1, 3 is 2 plus 1, 5 is 3 plus 2, and so forth and so on. But if I wanted to know, like the 171st term, I'd actually have to list out all the first 170 terms to find the 171st term, which is a pain. So there is no what we call explicit formula. We can't stick 171 into any known template to get that term in the sequence. But we can explain how the sequence behaves by using what we call a recursive formula. It's saying that any term can be found by adding the previous term and the term 2 terms before that. So that is a Fibonacci sequence. We are going to be asked to find templates for sequences. If there's not a template for a sequence, they won't ask you to find one. So, all right, explicit, recursive, examples of sequences. All right, let's look at one more. Let's look at this guy. Let's look at the sequence. 1 over n squared. All right, so if I list the terms of the sequence, the first term, if n was 1, it would be 1. If n is 2, 1 over 2 squared would be 1/4. 1 over n squared would be 1/9, so forth and so on. 1 over would be 1/16. So therefore, we can find an explicit formula here. It was actually given to us. The nth term is 1 over n squared. So if I wanted to know the 100th term, so the subscript just tells us what term in the sequence it is, it'd be 1 over 100 squared, so it'd be 1 over 10,000. All right, so once we have an idea how to create a sequence, or if we're given a sequence that's already created for us, we like to just talk about how these sequences behave. So let's just keep working on this guy, 1 over n squared. So we can graph these. Remember, sequences are just functions whose inputs are the natural numbers. 1 over n squared as a sequence behaves like the function 1 over x squared, but it's just not continuous. We're only going to look at it for inputs that are our whole positive numbers. So at 1, my output was 1. At 2, my output was 1/4. At 3, we're at a 9th. At 4, we're at a 16th. So what I'm interested in here is seeing how this sequence behaves. How does 1 over n squared behave as n goes to infinity? So we can clearly see as n goes to infinity, my outputs are going to, because the higher the number in the denominator, the outputs are going to 0. The higher the number in the denominator, we square it. It's going to create yet a bigger number, and the outputs are going to get closer and closer to 0. So we say 1 over n squared goes to 0 as n goes to infinity. Or we can say, let me see. Yeah, hold on. We're going to do this. We're going to say the limit as n goes to infinity of 1 over n squared equals 0. Or we can say 1 over n squared converges to 0. So that's where we're interested in, how these limits behave as n goes to infinity. What is their eventual behavior? So if you go back into your Calc 1 notes, look at the section on infinite limits. Limits at infinity. Sorry, infinite limits is when the output is infinite, but we're always going to be talking about how these sequences behave as n gets infinitely large. So let's formalize this. Okay, a sequence converges to L, where L is a finite number, if the limit as n goes to infinity of a n equals L. Now more formally, and I'll let you read this in your book, but typically we don't need to focus on this definition of a limit unless you plan on keep going on in your math studies. We'll use this more in higher level math, like in a real analysis class. But the formal definition of a limit is if for all epsilon greater than 0, there is an integer n such that eventually all the terms of the sequence fall within epsilon. So what does that mean? I'm going to go back to here. And it's saying no matter how small of an interval we choose around the projected limit, so this would be, this distance right here would be epsilon, this distance would be epsilon. Eventually, all the terms of the sequence would fall within a little tiny distance or a little interval around the output. So here, in this case, it looks like just from my diagram, for anything greater than 4, it would fall within. So no matter how small we chose this epsilon, we can make that really itty bitty tiny, eventually all the elements of the sequence would fall within that little band. So there's the formal definition of a limit. Again, we're not going to worry about that. I want you to be able to just find the limit, and we're going to use the directives that we used in chapter, back in, what was it, chapter 2 perhaps, the limits in our Calc 1 class. If a sequence does not converge to a finite number, we say it diverges. But being divergent can happen in different ways. So let's do example here. We say the sequence 1 over n squared converges to 0. And we can look at the Fibonacci sequence. 1, 1, 2, 3, 5, 8. Okay, these grow without bound, diverges. We can diverge in a different way, though. If you think about limits, maybe trig functions. Let's suppose we look at this sequence, -1 to the n power. We look at this, if n is 1, it would be -1. If n is 2, it would be +1. N is 3, it would be -1. So this is just the sequence that bounces back and forth between positive and -1. So this doesn't grow without bound. This diverges in a different way because it shoots up to infinity. This just bounces back and forth between -1 and 1. So it doesn't converge in on one particular value. So this diverges also. All right, so we are interested in this guy too. When a sequence grows without bound in this way, we say it diverges to infinity. Here we just say it diverges, period. It bounces back and forth between two constants. We have a definition for diverging to infinity. The definitions are a lot worse than the actual practice. We say that a sequence diverges to infinity if for any number we choose, any positive number we choose, eventually all the sequence elements are bigger than that number. So for the Fibonacci sequence, 1, 1, 2, 3, 5, 8, so forth and so on. If no matter what number we pick for, let's do this. Let's do 1, 2, 3, 4, 5, 6, right? And we're going to be at 1, 2, 3, 4, 5, 6, 7, 8. At 1, we're at 1. At 2, we're at 1. Here we're at 3, and we jump up to 5. At 5, we jump up to 8. And then we're going to jump up to 30. It kind of looks like it has exponential growth. And this says we can pick any number. And eventually, all the sequence terms will be above that number. So here I chose m to be relatively small, but even I could choose m to be something really large, like 1,000,000. And eventually, we could take the sequence out far enough where all the outputs would be above 1,000,000. All right, so I'm just going to refresh your memory on our limit theorems. All the limit theorems for functions apply to the limit theorems for sequences. Because sequences are functions, they behave just like their corresponding functions. We just restrict the domain to positive integer inputs. So if we have a sequence an that converges to A, another sequence Bn that converges to B, where A and B are both finite, then the limit of a constant times a sequence is just the constant times the limit of the sequence An. The limit of a sum is the sum of the limits. The limit of a difference is the difference of the limits. The limit of a product is the product of the limits. So again, these are just our calculus theorems. The limit of a quotient is the quotient of the limits. And we'll see these in practice as we work along. And the limit of a sequence to a power is just the limit to the power. And then you should have talked about the squeeze theorem in your calculus class. The squeeze theorem says that if you have a sequence bounded between two convergent sequences that converge to the same number, so an converges to L and Cn converges to L, and if B falls between A and C, then B must also converge to L. So let's suppose an behaved like this. Like an was this, and here it converges to L, so I might do some funny things, but eventually it converges into L, so that's an would be my red guy. And then let's suppose Bn also converges to L. And there's Bn in black. And then we have Cn, which falls between these two. Trying to find a color. Yeah, well, I'll do this one. So let's suppose Cn is between these guys. That one's in here. And then this guy falls between those two. This one falls between those two. That one falls between those two. So if both the pink and the black sequence converge, whoops, nope, sorry, black one would be Cn. I went out of order. And then Bn falls between A and C. So if B falls between A and C C both converge onto L, then the sequence B must also converge onto L. So when we need this, I'll refer back to it, but I'll say, oh, look back in your notes in 11.1, and you'll remember this guy, okay? All right, so let's keep going. Lots of definitions and stuff in this. A sequence is called bounded above, and again, most of this will become more useful as we need it a little bit later in chapter 11. A sequence is called bounded above if simply there's some number, any number, such that all these sequence elements fall below that number. So for example, the sequence 2 over n, which is 2, 1, 2/3, 1/2, 2/5, is bounded above by 2. Because all the sequence, the largest element is 2, everything is below 2. We could also say it's bounded above by 3 or 7 or 5 or whatever we wanted. But it's just bounded above, and because there is a number such that all the sequence elements fall below that. The Fibonacci sequence, 1, 1, 2, 3, 5, is not bounded above. There is no number such that all the sequence elements fall below it, but it is bounded below. So a sequence is bounded below if there's a number that all the terms fall above. And the smallest term is 1. They all fall above 1. Now notice the bound doesn't necessarily have to be a number in the sequence. Let's look at 1 over n squared, right, which was 1, 1/4, 1/9, 1/16, is bounded above by 1 and below by, well, these go to 0, they never hit 0, so it's bounded below by 0. We could also say it's bounded below by like -10, but we typically tried to go with the largest lower bound or the smallest upper bound. So then that leads us to this definition. A sequence is bounded, just bounded, if it's bounded both above and below. So if it's both above and below, we call this bounded. A sequence can be just bounded above, it can be just bounded below, but if it's both bounded above and below, it's called bounded. Can a sequence be neither bounded above or bounded below? Let's look at this guy. -1 to the n times n. How does this behave? Well, at 1 would be at -1. At 2 would be at +2. At 3 would be at -3. At 4 would be at +4. So this is a sequence of integers that alternate signs. So is neither bounded above or bounded below. Also, this sequence is called divergent. Since the limit is n goes to infinity of -1 to the n times n does not exist. Now we can't call this limit infinity or negative infinity because it doesn't go to infinity. Only the even terms go to infinity, the odd terms go to negative infinity, but it bounces back and forth like this forever and grows without bound. It doesn't eventually always shoot up or always shoot down. So this is a case where we would say the limit does not exist. All right, couple more definitions. Then we'll work on a couple of examples. A sequence is called increasing if each next term is larger than the previous term. So for example, 1, 4, 9, 16 is an increasing sequence. A sequence is decreasing if each subsequent term is smaller than the previous term. So 1, 1/2, 1 cubed, 1/4, forever is a decreasing sequence. And we're going to, again, need to know these definitions for future sections. We're going to often need to prove a sequence is increasing or decreasing. We can do this with either algebra or calculus. So to show 1/n is decreasing, so we can look at this and say, oh, common sense prevails. 1/2 is clearly less than 1. 1/3 is clearly less than 1/2. But to algebraically show this, well, we can say that, all right, so an is 1/n, right? So keep that in mind. So the n plus 1th term would be 1/n plus 1. Now we've got to show that that is less than that. So how can we do this algebraically? And this, it looks like common sense, and often the simpler examples are harder to see what's going on than the harder examples. But algebraically, we would say, well, we know that any number plus 1 is greater than a number, right? This is just an algebraic fact, right? And then we also have our rules of inequalities, that if one number is bigger than another, and if we take the reciprocals, property of inequality. So therefore, this is the n plus 1th term is less than the nth term. And an equals 1/n is decreasing. Okay, we can also show this using calculus. So an equals 1/n corresponds to the function f of x equals 1/x. And if we take the derivative, That's x to the negative 1, x to the negative 2, which is negative 1 over x squared. Let's take a look at this. Negative 1 over x squared. This is always negative, and x squared is always positive. So therefore, negative 1 over x squared is negative. So remember, we're only talking about n equals 1, 2, right? So therefore, f of x, since its derivative is negative, the function is decreasing. So therefore, we can conclude its corresponding sequence is decreasing. All right, so again, we're going to need, when we start doing series, we're going to need to do this. So it's going to be really super important. All right, so I'm going to end here because these videos take forever to download if they're too long, and I will do some common sequences in part 2. Thanks, guys.